Check one, check two.
Check.
Check one, check two. Does that sound funny out there, or is it okay?
Check.
A little hot? You bring us down 3 dB, thank you. Great. Check one, check two. Cool. Hello, everybody. Welcome. Thank you for coming. I'm Christian Burrows.
Ashley Blackmore.
Yeah. So very happy to be here. Thank you to Circle City Con for having us. First, I kind of want to get an idea. Does anybody have any Splunk experience? Anybody use Splunk? Cool.
All right.
Anybody use Jira? A little bit? Cool.
Okay.
Great.
So yeah, we're here from Atlassian Security Intelligence team. Our team handles incident response for security-related incidents within Atlassian. The work we do is mostly comprised of threat hunting, proactive and reactive alert writing, analysis and response to product vulnerabilities and exploits, as well as generic security analysis across many platforms, internal and external. Christian and myself are responsible for improving the system that the security intelligence team uses to create and manage alerts. Our most recent advancements are what we're here to talk about today. Yeah, so I have a background in security engineering. I was on the Atlassian product security team from its early stage for about 6 years. And I was always mostly focused on automation. I had the normal responsibilities, but that was my main focus the whole time. Now I'm working as a sort of a dev, shoulder to shoulder with the IR team, working on everything from process improvement to automated analysis and enrichment. I call this trenches development because it's located somewhere between platform development and security analysis, but it isn't really either. Most recently, I've taken an interest in revisiting serviceless tools because they offer a lot of power and flexibility, but they remain sort of low maintenance.
Cool. So my background is almost entirely incident response. Like my first day on my first security job was responding to WinNTI hacks, and so I started learning Splunk that day. I did breach detection system testing, so I've worked with a lot of IDSs, a lot of IPSs, and the reason I do what I do is because of the movie Hackers. Cool. Me? Sure. Cool. So just a few months ago, inside of the security intelligence team, we realized that we needed to start cranking out alerts at a much higher rate, with solid metrics that showed us just not where we were at the time, but where we wanted to go.
Cool. But the team was creating alerts with no naming convention. We had inconsistent source control, incomplete historical data. We didn't have a way of automatically measuring product coverage across the org. And alert knowledge and context was being kept in multiple silos, multiple places. Some alerts silently sitting broken in our configuration. We never knew about them. So we realized pretty quickly what we needed was like a robust pipeline that would allow us to scale up our team's alert production capability. So that's what we set out to build. So we set out to build one.
Cool. Cool. So today we create alerts with purpose. We observe where an Atlassian product or service has 0 alerts written for it for a given attack chain step, and we create alerts and set goals to turn those zeros into ones. Let me take these. Cool. So topics on the left are the sort of main problems that we decided to prioritize in finding a solution for. So this is what things used to look like. This should feel kind of like consternating and a little rough to look at. So what does disorder look like? So we had no naming conventions. It doesn't necessarily look bad. Like a lot of this is human readable, but it can look good and be disorderly. A lot of them were, human readable. You can kind of tell what's going on, but again, there's no real like programmatic or consistent way of naming these. So if you have a new hire, what do you tell them when they ask how they should name an alert? If you don't have a convention, how do you know what product or service or data source the alert is actually alerting on? Some of them have product names. How do you programmatically quantify what types of alerts you have across your infrastructure? So because we had no naming convention, we had no way of categorically organizing our alerts. They sit in Spunk next to other safe searches, and they were just being keyed off of the word play. So how do you know what types of attacks or situations you are alerting on for a given product? How do you find all of the related documents for each of these alerts. How do you know what coverage you have for a specific product? So Atlassian uses Bitbucket to house its Splunk save searches conf file. This is where all of our scheduled searches and detections go into. Keeping your save searches in Git may sound like work, but for us it was a step in the right direction. It allows us to revert mistakes, maintain a production trail, and get directly into the integration, or the continuous integration loop. So we're using source control, but at this point there are no rules, no standards, no protections, and commits are all over the place. As you can see, I mean, this is just anything and everything, no real order there. We could dig through these commits and look for comments, but, you know, have you ever written, like, not the best commit messages? Does a commit message always contain keywords that will be searchable later? Will they relate to the search you've just modified? And if you modify the search once or 100 times in source control, are you updating that search everywhere else in your org where it might appear? Documentation, you know, original source, things like that. So, writing queries in the Splunk UI is one thing. Freehand editing of Splunk queries inside of savesearches.conf is another, and can be very error-prone. If you've ever seen a Splunk stanza inside of savesearches.conf, and you're just going in willy-nilly editing things, it is error-prone. So, do you know that all of the searches that you have in there are actually working? Will you get an event from Splunk if they fail? Will Splunk even get to the point where it tries to run one of the queries? You think you're protected on this one query, and then it actually is never executed because of one, like, trailing space. Do you have a dedicated person who looks through the Splunk internal logs about scheduled searches and error logs, ever? Do you know the statuses of each error message and what they do?
Oh, I've got a mic already. So in summary, we had no standard. Validation was a manual step. We had patchy source control. Our searches were brittle, and we were trying to keep all of our data in sync across all of these information silos. One of the obvious problems here was that we had too many sources of truth. When an analyst adds a new detection, they may forget to create documentation. When they update a play that has documentation, they may forget to update that documentation. And obviously, you shouldn't have to go to 2 or 3 different places to get a full picture of what a single detection does. So what we knew we needed was a home for the detection so that we could track it, a way to aggregate the data so it could be distributed throughout a pipeline. We needed a way to store everything in source control, and we needed a way to document the detection. With all of this, we could ship that detection to Splunk and thereby create a pipeline. For us, the tools in this puzzle are Jira, Bitbucket, Confluence, and Spunk. The way we bring all these silos together into a single pipeline is through the use of a CLI tool that we call the Standardizer. With our source of truth being Jira, we knew that even though most of our ideas start in Splunk, they only really become concrete detections once they've found a home in Jira. That's sort of the way we've operated for a long time. But by now requiring our analysts to create alerts in that single place, we're able to control and normalize the output of all of the alerts. So to get to this point of Jira as single source of truth, we looked at the data that we would need at the input, in order to give us all of the outputs that we wanted at the other end. For example, we knew we needed a story to tell people about what the detection does. We wanted to integrate MITRE's attack framework so that we had a nice way of categorizing alerts. And of course, we needed the hard data, the Splunk search, the production dates, the authorship details, and so on. So what we did was we put each field we wanted into a custom Jira issue type, stripped everything else away, and the name we gave to this was core data. So when an analyst has their detection ready, they can kick off the standardizer process. Once the data is inside the process, we're able to start thinking about what kinds of standards we can enforce on it. We do this throughout the pipeline, from Jira to the standardizer process itself, all the way to continuous integration. For every field that we require, we're going to do some sort of validation, linting or mapping of those fields in order to generate a consistent quality-controlled alert. Once the processing is complete, core data ends up as a literal JSON blob on disk. We then take that blob and store it on Bitbucket on its own feature branch. Bitbucket pipeline is then used to run several layers of deep validation on the Splunk search. And once those build checks pass, we can finally merge that branch into our master Splunk config and ship it off to Splunk itself. The standardizer also transposes that data onto a new Confluence response page. Since this is done in serial, we can ensure that every detection always has up-to-date documentation by default. And once it's merged to Splunk, we've closed the loop. Alerts come back from each detection with the correct metadata, which means we can build great metrics. And of course, we've taken hours or even days off of the delivery of each detection by removing tons and tons and tons of busy work.
Cool. So since we're using our issue tracker to hold our detections and alerts, it starts to create a feedback loop and a lot of reciprocal linking. So since all of our alerts and detections documentation are labeled with the same key from the original alert in Jira, we're able to create metrics throughout the system, see alert coverage, frequency, and have all of those automatically linked to any incidents that come up as a result of these alerts firing. So this combined with the MITRE attack framework gives us a way of measuring our biggest attack vector based on the current coverage that we have. We're going to dive in a little bit deeper. Soup to nuts. So first we connect to Jira so that we can retrieve all detection from the Jira REST API. This just means querying Jira, pulling down that custom issue type, all the data from it, and then that's the beginning of a Python object for this. This is a snippet of the custom Jira issue type, which houses detections. We build the core data object from these fields. The core data concept was basically the idea that there was a set of information that started at the beginning, and then it permeated all the way through to the end. And so by controlling it at the beginning, we're making sure that it's basically perfect for us all the way through, and it exists everywhere. So this is a Python object that's going to be transformed and sent over the wire in various formats to populate the numerous outputs of the pipeline. We run validation on all of these fields before they're processed further. For example, the name structure. So let's see here. We check that the issue's short name is less than 48 characters. This is a somewhat rigid constraint, but it was that compromise that allowed us to arrive at a name solution that works for us on a daily basis. If validation fails for this field or any other field, we raise the linting failures to the user to be fixed. Instead of unknowingly submitting a broken detection upstream, which was happening, we stop the process here so the analyst can simply go back, fix any errors that were raised, and rerun the process. We also check that the field containing the attack tactic is a valid MITRE attack tactic. We do this by comparing it to MITRE's Cyber Threat Intelligence repo, which is a catalog of MITRE attack information expressed in STIX 2.0 JSON format, which we unpack on the fly. So this provides a degree of rigidity that forces the analysts to pick out a tactic that fits our model. If a tactic cannot be chosen, it may indicate that the analyst needs to reframe their detection query or even determine that it's out of scope.
We also check that the Splunk query field content. We also check that the Splunk query field content straight out of the Jira issue. Some of the validation is akin to a style guide in programming, but we do much deeper validation and testing on the Splunk search later on. So, for example, here we always want to check that earliest is in the query so that the analyst has time boxed their query every time. Once validators have run, we also run transformations on a number of fields. For example, we convert these human-readable schedules from Jira into cron expressions, which will later be used directly in the Splunk query. If anyone's ever worked on a large Splunk cluster alongside hundreds of other scheduled searches, they'll know that Splunk can get congested at specific times of day. We recognized that the load was negatively impacting Splunk's performance, so we identified off-peak times and rescheduled our searches to run at those times. This reduces load on the Splunk cluster, and we were able to do this because the Standardizer has programmatic control over the scheduling. So at this stage, we built the primary core data object, and now we move into secondary operations. These are things such as serializing the Jira issue for storage, building the name structure, and preparing the Splunk code, or Splunk queries. The name structure is built by taking the primary scope and attack tactic, the log location, and the short name. And once all these strings are sanitized, we just rip off an old AWS idea and concatenate them with double colons. This is later fed back into Jira to replace the original issue title. For the Splunk search, we strip whitespace on a line-by-line basis and format the whitespace to comport with RFC 822 message strings so that they comply with Splunk's multi-line configurations. And additionally, for each detection, we add the metadata from the alert, attack tactics to cross-reference the alert, as well as the results from the alert at the time that it fired. This allows us to preserve a long-term historical record of all the alerts in the form of summary indexes. Once the analyst has confirmed that the data processing we've done looks okay, we're able to take that data and distribute it to the various outputs. So what do these outputs look like?
So first we have confluence. This is, again, so you can kind of see this is a set of the core data. The benefit of having it in confluence is you have the ability for rich text editing if you need images, videos, things like that. So we've taken the prepared fields and rendered them to HTML using a Jinja template. We then submit this to the Confluence API, and Confluence gives us a lot out of the box for free, such as automatic cataloging, hierarchical nesting, metrics, and cross-product linking. The Jinja templating allows us to use Jira macros that automatically place these metrics on the page. Since everything is automatically labeled, we can easily retrieve the page by tactic, issue key, or product. So down there are some of these metrics that you get out of the box because you're able to just look at this original issue key that it came from. Then you can see how many times this issue has fired and what the result of it was. You would see things like false positive, true positive, test, etc. For each detection, Jira issue titles are updated to use an at-a-glance name structure. So you can name your Jira issue whatever you want at the beginning, but once you run it through the standardizer, based on the core data, that's what it's actually choosing the name off of. So you can take just a glance at that and know immediately what the detection is about. So our last major output is the submission of the search stanzas, which is in two parts. First, we make a submission to the alert blocks repository, which includes all core data, search stanzas, and test code for each detection. This is organized into a directory structure, first on scope, and then on, what was it?
Tactic.
And then on tactic. So basically, it just sits in a nice directory structure so that you can see first product, and then you can see the MITRE attack tactic that's used, and then every detection that exists underneath that same MITRE attack tactic. We use Python's config parser at this stage to both parse and write the config files. This allows us to validate that only one stanza is written to this particular file, as well as ensuring the config is compliant with the RFC. Each branch is named after author and issue key, and therefore we can look up existing detections at a later date and apply updates.
Once the alert blocks repo stanza is written, we have to insert the stanza into the main save searches conf file, which is somewhat more involved. Since we have a case here where multiple analysts are working on the same file, and since config files can have superficially repetitive content in the eyes of the git diff algorithm, we run the risk of running into merge conflicts. This can result in a lot of frustrating work during pull request reviews, and the approach that we took originally created a lot of these conflicts. We were just appending stanzas to the end of the file. Two analysts would be doing that at the same time, and because you have the similarity between the stanzas, the sort of same thing with JSON or whatever, Git gets confused. So the workaround for this is when inserting the new stanza, you parse the entire file, sort the stanzas by title, and then you rewrite the entire file. This results in a far lower likelihood of adjacent stanzas from separate contributors, and therefore better diffs. There's a much lower likelihood of merge conflicts. Finally, we print out the PR links for the analyst to click on and create in their browser, and from there, analysts can come in and sanity check the actual business logic of the queries.
Cool. So in parallel, every branch submitted to these two repos has its own CI plan running with the following stages. First, we install and configure a demo Splunk instance in a headless fashion with Bitbucket pipelines. So we use this instance to run Splunk's internal B tool across all of the newly created config to identify any configuration issues. If you haven't ever used B tool and you use Splunk, you should 100% use it. We go way beyond this basic configuration troubleshooting and we execute every single Splunk search at the pipeline's time. So when you make a commit, it's going to go through your entire save search comp and actually execute the Splunk search, each and every single one. Because while B-Tool will verify your configuration files are good, the only way to actually check Splunk's syntax that it's not failing is to run it. And you can't really run these in the UI. I actually figured out how to do it on the CLI, and it is sweet. So this allows us to catch any syntax errors, and again, that stuff would be caught at runtime. There'd be searches that had been there for a year, and there was just one apostrophe missing, or one quote missing, but we don't get any errors when it pushes up. It wasn't until we started actually running every single search in the CI that we were able to detect some of these like tiny little syntax errors. So we have multiple layers of validation occurring here from the beginning of the process all the way to the very end. When you first feed your issue into the pipeline, it validates the input, passes that input from stage to stage before resulting in the finished product. Production-ready queries with the assurance that our queries are truly ready. Doing all this validation and transformation manually for every query is difficult, tedious, and inefficient. And this pipeline eliminates all of it. During the whole process, we really only request human attention only at the point that it's required during the pull request. So you shouldn't have to be going in and checking for spacing or errors or linting or anything. So, in review, what are some of the big wins?
What are some of the big wins? Well, we now have a bird's eye view of security across our product suite and infrastructure. This is a huge win for organizational purposes and for metrics across the org. These metrics have application for multiple teams. And more generally, we see this framework as having applications outside of security, such as on abuse and fraud teams, or for certain types of SRE work. But really, I think this framework can work to drastically increase alert coverage and consistency for any team that's tracking anomalous activity across multiple products or silos. So what's next? So we want to build for each detection. We next want to build a matching test that triggers each detection. This lets us know that these tests are working, and it can help. And of course, it can help us catch regressions as a side effect. And we're working on generalization to make this more accessible to other teams and use cases. So open source is a goal. That means adding things like tool-agnostic interfaces, Markdown, and a full Docker framework.
We through that.
We did. Yeah.
So we have a demo we can pull up, and we have time for questions. But it's right for lunch, so I'm sure nobody cares that we're 20 minutes late, or 20 minutes early.
45. Yeah.
So I'm going to grab my laptop and grab that demo. In the meantime, Ashley will answer any questions anyone has.
Yeah.
Can you go back to that slide, the table with the missing detections and the fire check?
This?
Yeah, we call this the money shot. This is awesome. So you have your products, your scope over here. And again, this is all programmatically generated because of the core data that we request at the beginning. You have your naming convention, then you have the attack chain steps. Everything is labeled. So, I mean, when I showed this to a manager, they loved it. And it's cool, because then you can actually plan. Like this one needs to turn into a 1. It's simple. It allows you to actually create alerts with purpose and have, an idea and a plan instead of just guessing. Cool. You know what this is? Sure.
Oh, should I switch this out?
Yeah, I think so.
I think so. I just need just a tick.
I'm gonna pull off the side.
Seku.
Cool. So, I'm going to pull this up. Let's see here. Make this full screen. Cool. I'll try and talk over this. So this is the custom Jira issue type that we created. It is a play custom issue type. You want to pause it for a second? I'll just talk about this a little bit. So again, labels, that's where your MITRE attack tactic comes in. Short name. So the idea here is even though we're generating a programmatic name for the detection, we still wanted some human readable part. And that was where we did the 48 character limit on this. So that still should kind of be like, you should just be able to read what's going on. The data source, so this is, for us, this is like our Splunk event types or indexes. It's basically just the log source. Again, the attack chain steps, and then the scope. So this is what puts together the naming convention. This is what allows us to do metrics. This is what allows us to see cross-product coverage. We have the Splunk search in here. The response, so this is the thing that gets propagated out to the confluence page. So if an alert actually does fire on this, then when I get the results in Jira, because it comes back to Jira, there's a response page. So I write this alert. Ashley happens to be the one on call responding. And so he goes to the response page to go through the steps of what it is, because he doesn't necessarily have any context for this, as he's never either seen it or he didn't write it. And then again, the Splunk scheduling. This is that really sweet thing that Ashley did. So you have every hour, every 4 hours, every 12 hours, and then it converts it into a cron schedule at off-peak times on Splunk, so that we're reducing the load and making our Splunk team very happy. Cool.
Got some mouse action?
Yep, some mouse action.
All right.
Cool. So that's the issue key up there. So here's the command line tool, the standardizer. I type in the issue key. It goes and it pulls all this data back. This is an example of the validation failing because I didn't have a test description. So a test description is our future work, where we're going to be integrating actual like Python code and tests into it, so that if, let's say, my test is about a network connection on AWS from GuardDuty, then I go and spin up a server in China or somewhere else and make sure it connects outbound to that. So that would be the test. So that what we saw there, you can hit play. What we saw there was it telling us that this field was not filled out. So again, this is ensuring that every single detection that's created has all of the information that we want. Ashley made this very nice. So again, reconnecting after that little validation error. Cool. So at that point, it takes all of your data, makes sure it puts it into a cute little table. You can see how it looks, and you can pause it here. Thank you. So there you can see we converted the every hour. There's your cron scheduling authors taken from the assignee, which is me. This gets pushed into the Splunk stanza. So what we do is, like, this alert might suck that I just wrote. So for the first month, we reassign all issues that come out of this alert back to the original author. So this way, if I write a really crummy alert, it's not getting false positives all day to him while he's on call and I'm on vacation. They're all going to come to me. So again, this is the advantage of having a structured data source as your single source of truth for these. Cool, great. Okay, so then down here, does this information look correct? Yes, it does. So, do you want to create a new confluence page? Yes, I do. And the really awesome thing too is actually figured out how to update pages too without overwriting them completely, because we were kind of running into an issue where we couldn't really, if it existed already, it was kind of like, well, what do you do? And so we wanted to keep all of the information up to date. So when you update this here, I just run this again, and then it's going to update everywhere, including Confluence.
Yeah, we've got the Confluence page history because we're just maintaining the same page, and also by using the same branch names in Bitbucket, we're maintaining the history there. So we have an audit trail throughout everything, just by leveraging what those products inherently have.
So updating the issue summary. So what it's doing is it's creating the name structure out of this. So that original Jira issue said hello Circle CityCon. After it's done here, it'll end up saying GuardDuty, AWS, Tactic, et cetera, et cetera. And again, that just creates uniformity across the board. There are no wishy-washy, whatever kinds of play names. So it's creating pull requests for you. And oh yeah, the other great thing is because of the reciprocal linking, as it updates this Jira issue, it's going to insert the response link here. So in the way like Jira and Confluence work is anything that you do, if it's referenced or mentioned in it, then it starts linking it automatically in these, like, it's related to or is mentioned by. So then you just get this huge feedback loop where you have a trail of every single thing that you've done that's related to this. And when you create these pull requests, it actually goes into the Jira issue as well. You can see on the side, it's like number of pull requests, where they merged, where they declined, etc.
Yeah, and one of our Jira instances was a little slow this morning. I mean, Yeah, Jira.
Those are the VPN and hotel Wi-Fi.
Yeah. Real good.
Did you ever, is that what you want? The nice, like, sweet spinner? Did you ever update that?
Yeah, I couldn't get a little Doge.
Oh, you wanted the Doge spinner?
Yeah, it's not enough pixels there, unfortunately.
Cool. So yeah, so that was it shifting to a different repo. So we have it in two repos. One is the one that will be housing everything for the original, for the testing, right? So it's kind of a different structure. And then we also have one for the Splunk safe searches. So that goes into our app that we use within Splunk. There's your Confluence page. Go ahead. So that's there. It's been created. It drops itself into this hierarchy where we keep everything. And again, it's just core data persisted through. Yep. Go for it. You
extend it. Yeah. We have this blank box for the extended response because this is a fairly rigid format here. Oftentimes, analysts will want to write more comprehensive documentation with more rich text, images, videos, whatever it is. All they have to do is make a child page from this page, and it'll end up in the extended response box with the Confluence macros.
And yeah, so wait, pause real quick. Can you go back to Smith?
Oh, sure.
Yeah. Talked about it a little bit, but again, so here again, you have the reciprocal linking. Here it is. Because it's created and mentioned on this page, Jira issue is going to already be linked to this. And then down there, that's where the issues would be found, because this was a dummy detection that I made for this. There's no issues found, but if there were 10 or 20, you would see all the details about it, and like most recent ones done. And then you just have like a summary here, which just gives you numbers, like how many true positive, how many false positive. And then you get these nice little links just to go and create your PR. You can pause it a second if you want, whenever it goes. Mm-hmm. So it's already done everything. Nice thing, we can put this here. One of the things that we're going to do, when we came up with the idea just the other day, was have the kind of criteria for reviewing PRs, or the criteria for alerts, in that automatically generated inside that. Because we have guidelines and how we're supposed to review and improve these things. So that's, again, just the benefits of having it automatically generated for you. And so, once it gets down a little to the, cool, pause right here. So this is the Splunk stanza. They all look like this. They're all programmatic. You see the labels that we can add. Goes back to the original Jira key. Has the MITRE attack tactic. And these, when this alert fires, it goes into the Jira issue that gets created from the alert. So if I connect to this rogue server from my AWS thing, this thing detects it, it goes. It's going to add all those labels to a Jira issue as an alert. Right now, it's going to assign it to me. And once that gestation period's done and it's not a super bad alert, this will just go unassigned and drop into our queue. We pretty out the results using some markdown. Again, so here's the play link. So this goes back to that response page on Confluence that we saw. So that's in the Jira alert. There's your cron scheduling. I think that's pretty much. Oh yeah, you can stop right there too. So one of the other things. Whoa, she's gone. One of the other things was trailing spaces, trailing backslashes. So Ashley, can you explain the config parser part of Splunk Stanza?
Sure. So for our save searches conf file originally, we were it wasn't RFC 822 compliant. So basically we had a non-compliant config file, but it worked just fine in Splunk. Splunk sort of just lazily passed the config, and so what we did a little investigation, and we realized that it was just an RFC 822 config file, which is what Python's config parser parses. So we had someone volunteer to sort of go through every single stanza in our save searches conf and fix all of the trailing spaces. This meant that we could pass that file, and then basically each stanza just becomes an object in code, which means we can access any piece of it, change it. For example, changing how the cron schedule is set up, that we can just sort of jump in there and change that.
Perfect. Yeah, and that is the demo. That concludes that. And we're closer to our time now. So unless anybody else has any additional questions, thank you very, very much.
Thank you very much. Cheers.
That was the first time we talked about it. This is, he and I love working on this. It's been a lot of fun. So thanks for letting us figure it out. And we've learned a little bit about what kind of content and how much content we need.